So what the master method is, it's quite useful for analyzing the running time of recursive algorithms. So it's in some sense a black box, or an API if you like. It's a formula where you can solve these recurrences, and you just solve them in the most brain-dead way possible. You just plug in parameters, boom, out pops the number, like magic. Okay? So I will, of course, tell you what the master method is, and we'll evaluate it on the examples we've seen so far and some other examples. So you'll learn how to use it, but of course you're all going to be, card-carrying Stanford computer scientists. So I'm going to show you not just what it is and how to use it. I'm going to show you a little bit what's under the hood today, also. Okay, that's part of the rite of passage that is CS161. But moreover, I think that will give you a lot of intuition. I think if you just see this, it seems very mysterious. But I think if you understand what's under the hood a little bit, it's no longer very mysterious. In fact, even almost becomes obvious. So that is my goal for today, to make this seemingly mysterious formula almost obvious. So as I said, for the master method, we will assume that all subproblems have equal size. Okay, like in all the examples so far. Every time so far we've recursed on something with half of the input. We never recursed sometimes on a third of the input and sometimes on 2/3 of the input. Okay, so those kind of recurrences will not be treated by the master method. And suppose we have a recurrence of the following form. Okay? Or I should also say, so for this treatment of the master method, I'm deviating a little bit from the required textbook from Kleinberg-Tardosh. So there's a link on the website to a book chapter from a different algorithms book by Dasgupta, Papanicciu, and Vazirani, and I am following section 2.2 from that handout quite closely. So that's a very good reference for today's lecture. Okay? And so you should read that as well. All right, so the master method will deal with the following recurrences. So suppose we have a recurrence which looks like so. Okay, so T of n is at most A times T of n over B plus O of n to the D, and I'll discuss this in a second. Go through this slowly. So A here corresponds to the number of recursive calls. Okay, so we've seen examples 2, 3, and 4 so far. A could even be as small as 1. That's allowed. Okay, so A is going to be a positive integer. B is the sort of factor by which we shrink the input before we go to a recursive call. Okay, so far we've only seen shrinking by half, shrinking by a factor 2, but we'll allow other shrinkage factors as well. And if you want the algorithm to terminate, this better be bigger than 1. Okay, you better be passing to your recursive subcall something smaller than what you started with. So that's something strictly larger than 1. Again, we've seen 2 in the examples. And D, so far we've only seen the example of D equal 1. So D is the exponent in the running time of, I'm going to call it the combined step in some sense. So again, remember, in a recursive algorithm, there's work you do inside the recursive calls, and there's work you do outside the recursive calls. So I'm just saying, suppose the work you do outside the recursive calls has running time bounded by big O of n to the D. Okay, and D here could even be as small as 0. That would be constant time outside the recursive calls. So far we've seen d equal 1 where we were doing linear time work outside of the recursive calls. Okay? All right. So, again, I made a similar comment on Thursday. So A, B, and D, these are constants. And again, constant means independent of n. Do not ever apply the master method where you find yourself taking a value of A, B, or D that's a function of n. You're using it incorrectly. Okay? In the same way that the C's and the n naughts from Thursday should be independent of n. A, B, and D are constants. 2, 3, what have you. Okay, and then there's also a base case. So this is the non-base case, and for the base case, all that's important is that you have a constant size base case. Okay, so basically, T of n takes constant time for all n sufficiently small. And again, I'm being deliberately kind of vague because for the usual reasons, it just doesn't matter. Okay, so maybe your base case kicks in when n is 10 or less. That's fine. Okay, so it's not important that it kicks in at 1. Certainly the most common thing you'll ever see is T of 1 equal 1, but again, it just doesn't matter. Okay, so any base case where once the input size gets down to some constant number, say 10 or less, if it takes, say, 20 or less operations, you're good. Okay, that's fine. And this will cover everything we'll ever see in class, in homework, and so on. Okay, so you never have to be worried about whether or not this holds. I could cook up problems where it didn't hold, but I'm not going to do that for you in 161.